For 4.5 billion years, Earth has spun silently in the darkness of space, a pale blue dot cradled by a thin atmosphere, circling an ordinary star in a quiet corner of the galaxy. From a lifeless rock bombarded by fire and ice, it has transformed into a world bursting with life, colorful, intelligent, and breathtakingly complex. But this paradise was not born easily, nor has it endured without cost. Earth, for all its beauty, has a long history of destruction, a story not just of creation, but of devastation. Periods of unimaginable calm interrupted by moments of total chaos. Life has thrived here, but time and time again, it has nearly vanished. Entire species, entire ecosystems lost, not once, not twice, but again, and again, and again. We call them mass extinctions. Events so catastrophic, they rewrote the rules of life itself. 5 times in Earth's history, nearly all living things have perished. 5 times, evolution was forced to start over, and now, scientists believe we are in the midst of a 6th. But to understand where we are going, we must first look back, to the beginning. The Earth was born in violence. Around 4.5 billion years ago, a cloud of gas and dust collapsed under its own gravity, forming our sun, and from the leftovers, a series of rocky worlds. Earth was one of them. In its infancy, it was a hellish world, molten rock, poisonous gases, and constant bombardment from space. Oceans had not yet formed. There was no air to breathe, no continents, and certainly no life. But even in this chaos, the foundations of life were forming. Water arrived, perhaps carried by comet sand gathered in massive, steaming basins. Over time, the atmosphere thickened. Volcanoes released gases. Lightning, heat, and chemical reactions began to stir the primordial soup. Somewhere in those ancient waters, life began. We still don't know exactly how or where, but sometime around 3.8 to 4 billion years ago, the first living cells appeared. Simple, single-celled organisms, bacteria and archaea. Tiny, invisible, but incredibly resilient. For nearly 2 billion years, these microscopic life forms ruled the Earth. They filled the oceans, shaped the atmosphere, and even helped create the oxygen we breathe today. Then, around 2.1 billion years ago, a miracle occurred. Cells learned to cooperate. Some began living inside others, forming more complex structures. This was the birth of eukaryotes, the ancestors of all plants, animals, and fungi. And from there, evolution exploded. About 600 million years ago, multicellular life began to take hold in the oceans. Strange, soft-bodied creatures drifted through shallow seas. Then, around 541 million years ago, came one of the most important events in Earth's biological history, the Cambrian explosion. In a relatively short period of time, just 20 to 25 million years, life diversified rapidly. Creatures with hard shells, legs, eyes, and mouths emerged. The first predators appeared. Food chains formed. Arms races began. This was the dawn of complex ecosystems. For the first time, life became truly visible. But this explosion of life also set the stage for its downfall. Because evolution is not a straight path. It's a game of trial and error, of adaptation and failure. And the Earth itself is never truly stable. Its crust shifts, its climate changes. Its atmosphere thickens and thins. Volcanoes erupt. Seas rise and fall, sometimes slowly, sometimes catastrophically fast. And when these changes become too extreme, life pays the price. The first mass extinction struck around 443 million years ago. It would not be the last. Over the next 400 million years, life on Earth would be tested again and again. Species would rise to dominance only to be wiped away. Forests would spread and then disappear. Oceans would fill with coral reefs, fish, and ammonites only to be emptied by heat, cold, or poison. Each extinction was different. Some were caused by ice ages, others by supervolcanoes, some by sudden drops in oxygen, and one by a rock from space. Each time, the world ended for countless species. But each time, something new was born from the ashes. The story of Earth is not a story of death, but of rebirth. A story where destruction clears the way for innovation, where survival depends not on strength, but on adaptability, where the meek inherit the Earth not because they are mighty, but because they endure. Today, the fossil record tells us that 99.9% of all species that have ever lived are gone. And now, in the 20th century, scientists warn that we may be entering another great extinction, one not caused by volcanoes or asteroids, but by ourselves. Humanity has become a force of nature. We cut down forests, drain wetlands, overfish oceans, and pump the sky full of carbon. In just a few centuries, we have altered the planet faster than most natural processes ever could, and the consequences are already unfolding. But the story is not over. In this documentary, we will travel back in time to witness the 5 great mass extinctions of Earth's past. We will explore the causes, the chaos, and the aftermath of each one. We'll meet the creatures that lived, the ones that died, and the few that somehow survived it all. We'll uncover how each extinction reshaped the Earth, giving rise to new worlds and new life. From the silent tombs of ancient oceans to the fiery plains of volcanic wastelands, we will walk through history's darkest hours. Because to understand how fragile life is, we must understand how often it's nearly ended. This is the story of extinction, and how it gave birth to everything that lives today. Life on Earth has never followed a simple, uninterrupted path. Instead, its history has been shaped by repeated disruptions, events so severe, they didn't merely prune the tree of life, they nearly uprooted it. Scientists call these events mass extinctions, periods in which the diversity of life collapses on a global scale. These are not localized die-offs or seasonal disruptions. They are planet-wide resets, rapid, catastrophic shifts in climate, chemistry, or geology that erase the majority of living species in a geological instant. In each case, ecosystems collapsed, food webs disintegrated, entire classes and families of organisms vanished forever, but the Earth didn't remain empty. After each extinction, life rebounded, evolving along new lines, filling freshly abandoned niches, and, in doing so, reshaping the entire biosphere. These biological resets are rare, but they are not random. They leave behind a signature in the geological record in sediment layers, fossil distributions, and isotopic anomalies. And when studied together, they reveal a sobering truth. Extinction is a fundamental part of Earth's evolutionary engine. Without these interruptions, there would be no dinosaurs, no mammals, no humans. Extinction clears the slate, and what follows is not a return to what was, but the emergence of something entirely new. Earth hasn't always been alive. In fact, for nearly 500 million years after its formation, our planet was a hellscape, battered by meteorites, scorched by solar radiation, its atmosphere thick with toxic gases. But even in this chaos, something extraordinary was stirring. Roughly 3.8 to 4 billion years ago, in the depths of Earth's oceans, perhaps near deep-sea hydrothermal vents, or in the warmth of tide pools, the first living organisms emerged. They were astonishingly simple. Prokaryotes, tiny single-celled organisms with no nucleus, no complex structures. These cells were the very first life forms, and they would remain Earth's only inhabitants for more than 1 billion years. They didn't need oxygen. In fact, for them, oxygen was poison. These early microbes thrived in an anoxic world, a planet with no breathable atmosphere, no ozone layer, and no complex ecosystems. They fed on chemicals, absorbed minerals, and reproduced asexually, creating endless copies of themselves. Life was small, but it was persistent. Then, a group of these organisms evolved a superpower: photosynthesis. Cyanobacteria, sometimes called blue-green algae, began to use sunlight to produce energy, releasing oxygen as a byproduct. At first, that oxygen built up in the oceans, oxidizing iron into rust and forming massive iron deposits that we mine today. But eventually, the oxygen escaped into the atmosphere. This triggered the first global environmental crisis, often referred to as the Great Oxidation Event, around 2.4 billion years ago. For many organisms, this new oxygen-rich world was deadly. But for others, it was an opportunity. Around 2 billion years ago, the next evolutionary leap occurred: eukaryotes. Unlike prokaryotes, these cells had internal structures, including a nucleus and organelles like mitochondria. In fact, mitochondria may have once been independent bacteria themselves, absorbed by larger cells and repurposed as energy factories in a remarkable act of symbiosis. Eukaryotes were the foundation for all complex life. Over the next several 100 million years, they diversified and slowly began to cooperate, forming the first multicellular organisms. Life was no longer limited to microscopic individuals. Now, cells worked together, specialized, and formed tissues. With this, life gained size, shape, and structure. But for a long time, evolution moved slowly. Earth's climate swung between extremes: frozen snowball Earth episodes and hothouse periods. It wasn't until around 600 million years ago, during the Ediacaran period, that multicellular life began to flourish. These early organisms were soft-bodied and strange, resembling jellyfish, fronds, and quilted mats preserved only in rare fossil imprints. Still, the groundwork was being laid for something far more dramatic. Then, around 541 million years ago, something changed, rapidly. Within a few million years, a blink in geological time, life exploded in diversity. This was the Cambrian explosion, and it marks one of the most profound transitions in the history of life. Before the Cambrian, most animals had no hard parts, no shells, no bones, no claws. Afterward, the oceans were filled with creatures that were armored, jointed, and mobile. Predators and prey, swimmers and burrowers. The first complex food webs emerged. Many scientists believe this sudden diversification was driven by a combination of factors: rising oxygen levels, which allowed for higher metabolic rates and larger bodies; evolution of vision, which may have triggered an evolutionary arms race between hunters and the hunted; genetic complexity, including the development of Hox genes, which allowed organisms to build more elaborate body plans. The fossil record from this time is rich with bizarre and wonderful creatures. One of the most iconic is Anomalocaris, a meter-long predator with grasping limbs and a circular mouth filled with serrated plates. It ruled the Cambrian seas as one of the first apex predators. There was Opabinia, which had 5 eyes, a backward-facing mouth, and a long, clawed proboscis. Scientists still aren't quite sure where to place it on the evolutionary tree. Then came the trilobites, early arthropods, with segmented bodies and hard exoskeletons. They were incredibly successful, evolving into thousands of species and surviving for over 270 million years. In the shadowy mud lived Wiwaxia, covered in scales and spines, and Hallucigenia, walking on stilts with tentacles sprouting from its back. These creatures were evolutionary experiments, many of which had no direct descendants. But others gave rise to major animal groups we know today: arthropods, mollusks, annelids, and even chordates, the lineage that would eventually lead to fish, reptiles, birds, and mammals. The Cambrian explosion wasn't just a moment of creativity, it was a revolution in biology. It marked the first appearance of skeletal structures, complex nervous systems, compound eyes, and active predation. It changed how animals moved, how they sensed their environment, and how they interacted. Evolution was no longer crawling, it was running. Fossil sites like the Burgess Shale in Canada and the Chengjiang Biota in China offer astonishing windows into this ancient world. In some cases, even soft tissues, muscles, eyes, digestive tracts are preserved in exquisite detail. What they reveal is that by the end of the Cambrian, most of the fundamental body plans seen in animals today had already evolved. The blueprint for modern biodiversity was now written in stone, literally. But there's a catch. For all its brilliance, the Cambrian explosion was just the beginning. Evolution had taken life to new heights, but extinction would soon test its resilience. The oceans were thriving, but they were also changing. As continents shifted and climate fluctuated, entire ecosystems faced collapse. Some of the most successful Cambrian lineages would vanish in the Ordovician. Others would survive only to fall later. And so, the stage was set for a new pattern. Evolution followed by extinction, then renewal and innovation. This cycle of creation and destruction would become the heartbeat of life on Earth. What makes the Cambrian explosion so remarkable is not just how quickly it happened, but what it tells us about life's potential. Given the right conditions, evolution can generate an astonishing array of solutions. Some elegant, some strange, all adapted to survive. It also reminds us of life's fragility. The creatures of the Cambrian were real, complex beings. They lived, hunted, fed, and died. And many are gone now not because they were flawed, but because Earth changed faster than they could. The Cambrian was a time of promise. But nature, as always, had other plans. From the depths of time, life had emerged triumphant. But in Earth's story, every high has a fall, and the first extinction was waiting just ahead. For hundreds of millions of years, life was almost entirely marine. The land was still barren, a silent expanse of rock and wind. But in the oceans, life had achieved unprecedented complexity. During the Ordovician period, around 485 to 443 million years ago, Earth was a water world filled with a rich mosaic of biodiversity. Ancient coral reefs flourished along continental shelves. Brachiopods, trilobites, crinoids, and early mollusks formed vast benthic ecosystems. Planktonic species dominated the upper ocean layers, supporting a food web that extended from filter feeders to agile cephalopods, some stretching several meters in length. But change was brewing slow, subtle, yet catastrophic. Around 447 million years ago, the first signs of environmental instability appeared. What had been a greenhouse world began to cool. This wasn't a minor fluctuation, it was a full-scale glaciation. Earth entered one of its most severe ice ages, a frozen catastrophe that would forever alter the course of evolution. Gondwana, the ancient supercontinent that today forms parts of South America, Africa, Australia, and Antarctica, drifted toward the South Pole. There, a massive ice sheet began to form. As glaciers expanded, they locked away trillions of tons of water, causing global sea levels to plummet by over 100 meters. This sea level drop was devastating. The vast, shallow marine shelves, where most Ordovician life thrived, were drained, turned into lifeless plains. Coral reefs died off. Coastal habitats vanished. Filter-feeding organisms that relied on stable currents and nutrient-rich shallows perished en masse. While climate change is the primary suspect, some scientists have proposed a more exotic and terrifying possibility: a gamma-ray burst. Gamma-ray bursts are the most energetic explosions in the universe, caused by the collapse of massive stars or the merger of neutron stars. If one occurred in our galactic neighborhood even 0 light-years away, its effects would be apocalyptic. In this theory, A GRB stripped away Earth's ozone layer in seconds, exposing the surface to lethal ultraviolet radiation. This would have devastated plankton at the base of the food chain and triggered a cascade of extinctions across marine ecosystems. Although no direct evidence of such a burst remains, the idea serves as a sobering reminder that extinction threats don't always come from within. Regardless of the trigger or combination of them, the result was cataclysmic. Over the course of roughly 1 to 2 million years, Earth experienced two pulses of extinction, the first from rapid cooling and glaciation, the second from the subsequent warming phase when glaciers melted and sea levels rose again, causing anoxic events, massive die-offs due to oxygen-poor oceans. By the end, 85% of all marine species were gone. Entire lineages vanished. Reef builders, once dominant, were nearly erased. Graptolites, tiny colonial animals that floated in the open ocean, were decimated. Trilobites suffered massive losses. Brachiopods and bryozoans collapsed in diversity. Even the resilient nautiloids saw steep declines. This was Earth's first known mass extinction, and it revealed a pattern that would repeat throughout the planet's history. Biodiversity rising to astonishing heights, only to be abruptly reset by environmental catastrophe. Not everything died. Some organisms clung to life in isolated ecological pockets, deep basins, warmer waters near the equator, or sheltered continental margins. Among the survivors were jawless fish, such as the ostracoderms, simple vertebrates that had begun to explore new ecological niches. These early fish would eventually give rise to jawed species, paving the evolutionary road towards sharks, bony fish, and eventually land-dwelling vertebrates. Also spared were some hardy algae and the earliest non-vascular plants, which had just begun colonizing the damp margins of land. Though primitive, they were the pioneers of the future greening of Earth's surface. Some mollusks, echinoderms, and benthic feeders adapted to deeper, more stable environments. These survivors weren't necessarily the most complex or advanced, but they were adaptable, resilient, and lucky. After the ice retreated and the climate stabilized, life slowly returned to the seas. But the world it came back to was profoundly different. It took roughly 5 million years for biodiversity to rebound to pre-extinction levels. In that time, new species evolved to fill the empty ecological niches left behind by extinction. This rebound wasn't immediate, nor was it smooth. It was shaped by ongoing climatic fluctuations, changing ocean chemistry, and the slow reshaping of Earth's continents. One major evolutionary shift that emerged in the aftermath was the Silurian radiation, a burst of new species, particularly among jawed fish, coral-like organisms, and predatory arthropods. Terrestrial ecosystems also began to evolve, albeit slowly. The earliest land plants, likely simple liverwort-like organisms, spread across moist ground, paving the way for the complex forests that would arise hundreds of millions of years later. These pioneers played a critical role in stabilizing soils and affecting atmospheric CO2 levels, subtly shaping climate and setting the stage for more terrestrial life. The Ordovician-Silurian Extinction wasn't just a biological reset, it was a test of life's flexibility. Species that had evolved to fit very narrow niches, specialists, were hit hardest. Generalists, who could tolerate a wider range of environments, fared better. This pattern would echo in future extinctions. Evolution favors efficiency, but when disaster strikes, adaptability trumps perfection. This extinction also marked the first time Earth's biosphere experienced a global crisis with planetary feedback loops, glaciation begetting sea level change, climate altering ocean chemistry, extinction reshaping the trajectory of evolution itself. It was, in essence, the first rehearsal for mass extinction on a planetary scale. Today, We often think of extinction as something rare, the loss of a species here or there. But Earth's deep past tells a different story. Extinction is not an anomaly. It is a natural, though catastrophic, part of the evolutionary cycle. The Ordovician-Silurian event reminds us that climate can change rapidly, and those changes can have devastating consequences. Biodiversity can collapse even without asteroid impacts or volcanic eruptions. Life rebounds, but it takes time, often millions of years. And perhaps most importantly, it reminds us of the fragility of ecosystems, no matter how rich or stable they may seem. In the blink of a geological eye, entire worlds can vanish. The Devonian period, spanning from about 419 to 359 million years ago, is often celebrated as the age of fish. The oceans teemed with astonishing variety, some familiar, some alien. Coral reefs stretched for miles across shallow continental shelves, and jawed fish dominated the seas with powerful armored bodies and specialized teeth. Placoderms, the heavily armored predators of the time, had become the undisputed rulers of the underwater world. But the Devonian wasn't just about the oceans. It was a time of transition, a moment when life was beginning to shift from sea to land in a way that would forever change the planet. Plants were among the first pioneers. From small mosses and liverworts, the flora of the Devonian evolved into large vascular plants. Forests of early trees like Archaeopteris, with true wood and deep root systems, began to cover the land. These plants altered the atmosphere by pulling in vast amounts of carbon dioxide and releasing oxygen. They reshaped the soil, accelerated erosion, and funneled nutrients into rivers and seas. At a glance, this appears to be a story of progress, of life thriving and spreading into new environments. But hidden in this success was the beginning of a global crisis. The rapid spread of plant life introduced a wave of ecological changes. As roots burrowed deeper, they broke down rocks and released nutrients like phosphorus and calcium into the water systems. These nutrients, once washed into the oceans, triggered massive algal blooms. On the surface, these blooms may have looked like signs of abundance. But as algae died and sank, their decomposition consumed oxygen from the water, creating widespread dead zoniza phenomenon known as oceanic anoxia. Without oxygen, marine animals couldn't survive. These anoxic conditions began to stretch across vast regions of ocean, disrupting the delicate balance that marine life depended on. Species that had once thrived in stable, oxygen-rich environments began to die out. Coral reefs, once the backbone of marine biodiversity, started to collapse. While oxygen levels were plummeting in the seas, another force was at play in the skies. Volcanic activity during the late Devonian released large quantities of carbon dioxide and methane, heating the planet and contributing to climate instability. Some researchers believe that eruptions from the Vilui traps in modern-day Siberia played a significant role in these changes. The combination of volcanic gases and declining carbon dioxide from widespread plant growth created a tug-of-war between warming and cooling. The climate began to fluctuate unpredictably. Sea levels rose and fell. Ocean circulation patterns changed. Ecosystems were forced to adapt to rapidly shifting conditions, and many simply couldn't. What makes the late Devonian extinction particularly unique is that it wasn't a single, cataclysmic event like an asteroid impact. Instead, it was a drawn-out collapse. A series of extinction pulses occurred over roughly 20 million years, culminating around 372 million years ago at the boundary between the Frasnian and Furmenian stages. This slow-motion disaster wiped out approximately 75% of all marine species. Coral reef systems were among the hardest hit. Entire reef ecosystems vanished and would not return for over 100 million years. The extinction decimated placoderms, erasing the dominant armored fish of the era. Trilobites, which had already begun to decline, lost many of their remaining species. Ammonoids, conodonts, brachiopods, and other marine invertebrates experienced massive losses. But the extinction didn't stop at the shoreline. For the first time in Earth's history, terrestrial ecosystems began to show signs of collapse. Early land-dwelling arthropods and plants, once gaining a foothold, now faced a hostile environment. The very forests that had revolutionized the Earth's carbon cycle were beginning to die. With the disappearance of dominant plant species, the food web on land began to unravel. Even as ecosystems fell apart, a few groups managed to hang on. Among them were the lobe-finned fish organisms with strong, muscular fins and primitive lungs. These adaptations may have allowed them to survive in stagnant, low-oxygen waters. From these survivors would eventually emerge tetrapods, four-limbed vertebrates that would go on to colonize land and give rise to all amphibians, reptiles, birds, and mammals. In this way, the extinction didn't just mark an end, it also set the stage for new evolutionary paths. But the question remains, what exactly caused this prolonged catastrophe? Scientists point to several interwoven factors. Oceanic anoxia likely played the central role. The nutrient overload from terrestrial plant life, coupled with increased organic matter and poor ocean circulation, led to oxygen-depleted seas. At the same time, the expansion of forests may have triggered a significant drawdown of atmospheric carbon dioxide, cooling the planet and disrupting climate patterns. Volcanic activity injected carbon dioxide and methane into the atmosphere, adding bursts of warming that further destabilized the climate. Sea level fluctuations periodically drained shallow marine habitats, exposing coral reefs and shallow ecosystems to desiccation and extinction. It was not one killer, but many. Each event alone might have been survivable. Together, they overwhelmed life's resilience. Unlike the more well-known extinction events, such as the one that killed the dinosaurs, the Devonian extinction was quiet. It unfolded slowly, often invisibly, giving the illusion of stability even as species after species vanished. This slow decline has a modern parallel. Today, Earth is again seeing dramatic changes in nutrient cycles, climate systems, and ocean oxygen levels. And just like in the Devonian, many of the forces are subtle, cumulative, and human-driven. The Devonian warns us that extinctions don't always happen in an instant. Sometimes they creep in silent, steady, and unstoppable. Yet in the aftermath, life continued. Evolution filled the empty spaces left behind. Jawless fish gave way to jawed fish. Lobe-finned fish began to crawl, and the first vertebrates stepped onto land. The extinction erased much, but it also reset the board. And in doing so, it created the conditions necessary for the rise of the vertebrates that would one day walk, fly, and think. What began as a golden age of biodiversity in the oceans ended in silence. The world turned greener, but more fragile. And once again, Earth reminded life of its most fundamental rule: nothing is permanent. Everything changes, and those who adapt will inherit what remains. Roughly 252 million years ago, Earth witnessed its most cataclysmic biological crisis, the Permian-Triassic Extinction event, ominously referred to by scientists as the Great Dying. This wasn't just another period of ecological change, it was a planetary cataclysm that forever reshaped life on Earth. The numbers alone are staggering. Around 96% of all marine species and approximately 70% of terrestrial vertebrate species vanished. Forests collapsed, entire evolutionary lineages were erased, and ecosystems across land and sea disintegrated into silence. To understand the magnitude of this extinction, we need to explore the world as it was during the late Permian. The supercontinent Pangaea dominated the globe, bringing with it immense deserts, inland and extreme climates. Life had diversified tremendously, particularly in the oceans. Marine ecosystems teemed with brachiopods, trilobites, ammonoids, and an array of spiny, shelled organisms. On land, vertebrates such as synapsid-zearly relatives of mammals roamed the dry terrain, while ferns and seed-bearing plants provided green cover. But this biodiversity was about to be annihilated by a complex chain of geological and atmospheric catastrophes. Central to this mass extinction was the Siberian Traps, a massive region of volcanic rock in present-day Russia. One of the largest volcanic events in Earth's history occurred here, spanning nearly 1 million years. It released colossal volumes of lava, but more critically, it pumped unprecedented amounts of carbon dioxide and methane into the atmosphere. These greenhouse gases rapidly elevated global temperatures. The cascading effects were profound. The average global temperature soared by an estimated 8 degrees Celsius, fundamentally altering Earth's climate systems. Oceans became warmer and more acidic, dissolving carbonate shells and wreaking havoc on calcifying organisms. The warming also depleted oceanic oxygen levels, leading to widespread marine anoxia zones, where only the hardiest microbes could survive. Another devastating phenomenon was the disruption of the carbon cycle. As organic matter decomposed in low oxygen conditions, vast quantities of methane were released from methane clathrates frozen in seabeds. Methane, being an even more potent greenhouse gas than CO2, exacerbated the planet's fever. It became a vicious feedback loop. Warming oceans released methane, which caused more warming, further reducing oxygen levels. This environmental cascade led to what we now term the super greenhouse effect. The oceans turned sluggish and stratified, separating into distinct temperature layers with little vertical mixing. This caused the deep sea to become a repository of hydrogen sulfide, produced by bacteria thriving in anoxic waters. Eventually, some scientists theorized that this toxic gas reached the surface and escaped into the atmosphere, contributing to terrestrial die-offs and depleting the ozone layer. The fossil record confirms the abrupt disappearance of a vast range of life forms. Coral reefs, then composed of rugose and tabulate corals, collapsed. Brachiopods, once dominant in shallow marine ecosystems, were reduced to a few surviving lineages. Trilobites, one of the most iconic and diverse arthropods, were completely wiped out. Ammonoids, sea scorpions, and many early fish lineages saw catastrophic losses. On land, the devastation was no less dramatic. The lush forests of the Permian gave way to barren landscapes. The extinction decimated the dominant herbivores and predators alike. Synapsids, which had once thrived, were reduced to a few surviving genera. Terrestrial ecosystems faced a kind of ecological reset, with microbial mats spreading in areas once covered by complex vegetation. The recovery from the Great Dying was painfully slow. It took nearly 10 million years for biodiversity to rebound to pre-extinction levels, and the ecosystems that emerged in the Triassic period were fundamentally different. New groups, such as the Archosaurus precursors to dinosaurs and modern birds, began to rise. Marine ecosystems saw the rise of new reef builders, like sponges and scleractinian corals, and the early ancestors of marine reptiles began to appear. By the end of the Triassic period, the Earth looked very different from the chaotic world that had emerged from the Permian extinction. It was a time of recovery and reconstruction. Life had begun to rebound. New ecosystems had formed. Reptiles diversified into various groups, including the early relatives of dinosaurs, crocodilians, and marine reptiles like ichthyosaurs and plesiosaurs. Mammal-like creatures, small, warm-blooded, and nocturnal, also began to appear in greater numbers. The continents were still united in a single supercontinent known as Pangaea, stretching from pole to pole. It created vast arid interiors and long coastal margins. The world's climate was extreme hot, dry, and marked by strong seasonal shifts. And while life was clawing its way back from previous cataclysms, it was once again approaching the brink. The Triassic-Jurassic Extinction, which occurred around 201 million years ago, marks one of Earth's 5 great mass extinctions. It wiped out around 80% of all species and fundamentally reshaped life on land and in the oceans. But more importantly, it opened the door for a new kind of ruler, the dinosaurs. Unlike the slow, drawn-out nature of the late Devonian extinction, the Triassic-Jurassic collapse appears to have been sudden and violent, and once again, the Earth's own internal forces were likely to blame. At the heart of the extinction was a period of massive volcanic activity. As Pangaea began to break apart, rifts formed across what is now the Atlantic Ocean. These rifts weren't passive, they were the birthplaces of titanic volcanic eruptions. The Central Atlantic Magmatic Province, or CAMP, became one of the largest volcanic regions in Earth's history. Over a span of less than 1 million years, these eruptions released unimaginable amounts of lava across thousands of kilometers, covering entire regions in molten rock. But it wasn't the lava that triggered extinction, it was the gases. These eruptions belched vast quantities of carbon dioxide and sulfur dioxide into the atmosphere. Carbon dioxide trapped heat, driving rapid global warming. Meanwhile, sulfur dioxide combined with water vapor to form sulfuric acid, creating acid rain that devastated plant life. The combination of extreme heat, acidified rain, and destabilized ecosystems created a chain reaction across the planet. Forests withered, photosynthesis faltered, food chains collapsed. Animals that couldn't adapt to rapidly changing climates began to vanish. In the oceans, things were no better. Rising temperatures decreased the solubility of oxygen in water, leading to oceanic anoxia just like in the Devonian. Many marine species, particularly those in shallow coastal environments, suffered heavily. Ammonoids, bivalves, conodonts, and marine reptiles experienced major losses. Coral reefs, which had just started to recover from the previous extinction, were hit hard again. But what truly makes this extinction stand out is the turnover on land. During the Triassic, several groups of large reptiles, not dinosaurs, dominated the ecosystems. These included the pseudoseuchians, a diverse lineage of archosaurs that were close relatives of modern crocodiles. They ruled the terrestrial world with powerful limbs and predatory jaws. There were also mammal-like reptiles known as therapsids and large amphibians lingering in swamps and rivers. Most of these groups were wiped out during the extinction. Whether due to climate instability, vegetation collapse, or shifts in atmospheric oxygen, they couldn't survive the dramatic environmental upheaval. Their disappearance left a power vacuum, an empty ecological stage waiting to be filled. And in that void, dinosaurs rose. Dinosaurs had already evolved by the late Triassic, but they weren't dominant. They were mostly small, bipedal, and relatively rare. But after the extinction removed many of their competitors, they rapidly diversified. With fewer rivals and new ecological niches to explore, they expanded in size, variety, and habitat. In the Jurassic period that followed, dinosaurs would become the undisputed masters of the land. They would grow into towering sauropods, swift theropods, and heavily armored herbivores. Their rule would last for the next 135 million years. But why did dinosaurs survive when others didn't? One theory points to their physiology. Dinosaurs may have been warm-blooded or semi-warm-blooded, giving them an edge in fluctuating climates. Their upright posture and efficient respiratory systems may have allowed them to cope better with low oxygen and high temperatures. They were fast, mobile, and adaptable traits that are essential in times of crisis. Meanwhile, early mammals, though small and relegated to the shadows, also survived. They likely fed on insects and plants, allowing them to avoid direct competition with larger animals. Their small size and burrowing behavior may have helped them ride out the worst environmental changes. The extinction also had profound effects on plant life. Many seed ferns and primitive gymnosperms disappeared. In their place, new plant groups began to rise, including early conifers, ginkgos, and cycads. These changes would shape the landscapes of the Jurassic, providing new food sources for evolving herbivorous dinosaurs. Some scientists have suggested that an asteroid impact may have played a role in this extinction, though the evidence remains inconclusive. Unlike the later impact that ended the reign of the dinosaurs, the Triassic-Jurassic Extinction lacks a definitive crater or iridium layer. Still, it's possible that Earth was struck during this turbulent time, adding to the chaos already unleashed by volcanic forces. Whatever the exact cause, the result is clear. 80% of species were gone, reefs collapsed, marine ecosystems were stripped down, entire reptilian lineages were erased, and in their place, a new world began to take shape. The age of dinosaurs was not born in peace, it rose from ashes. This extinction marked a turning point in Earth's history. It wasn't just about loss, it was about opportunity. When old systems break down, evolution responds. What survived evolved, and what evolved began to shape the Earth in new and spectacular ways. The Triassic-Jurassic Extinction reminds us that extinction is not the end of life, it is the reshaping of life. It is an evolutionary crucible in which the most adaptable emerge stronger. In this case, it gave rise to one of the most iconic and successful groups of animals ever to walk the planet. It cleared the stage for an era of giants. 66 million years ago, Earth was a planet thriving with life. Dinosaurs roamed its vast continents, towering sauropods grazed endlessly in lush forests, and pterosaurs soared above while marine reptiles like mosasaurs and plesiosaurs dominated the oceans. But this flourishing Mesozoic world was about to face a catastrophe of unimaginable magnitude, an event that would mark the end of an era. It began with a silent object hurtling through space. Measuring approximately 10 to 12 kilometers in diameter, the asteroid that would later form the Chicxulub crater was large enough to disrupt global ecosystems in a matter of hours. It struck Earth with the force of over 1 billion nuclear bombs, impacting the shallow seas near what is now the Yucatan Peninsula in Mexico. The moment of impact was instantaneous and violent. A blinding flash lit the skies, followed by shockwaves that radiated across the planet. The Earth itself trembled. Tectonic plates shifted. Massive tsunamis swept across coastlines. The energy released was so immense that rocks from the impact zone were vaporized and launched into the atmosphere, re-entering the atmosphere as molten projectiles. These projectiles rained down, igniting wildfires on a global scale. Within hours, much of Earth was ablaze. The soot and ash from the fires, combined with dust and aerosols thrown up from the impact, formed a thick blanket in the atmosphere. Sunlight was blocked out, plunging the planet into darkness. Temperatures dropped rapidly, initiating what scientists describe as a nuclear winter. This sudden and prolonged absence of sunlight brought photosynthesis to a halt. Plants died en masse. With plant life gone, herbivores began to starve, and carnivores soon followed. The collapse of the food chain was swift and merciless. The oceans suffered too. The same aerosols and debris that darkened the skies also rained into the seas, acidifying them and disrupting marine ecosystems that had thrived for over 150 million years. Marine reptiles, including the once mighty mosasaurs and long-surviving plesiosaurs, perished as their prey dwindled and ocean chemistry shifted. Plankton, the base of the marine food web, suffered devastating losses, initiating a chain reaction that echoed through every level of the food chain. Coral reefs collapsed. Coastal habitats turned barren. The extinction was not selective. It struck indiscriminately across taxa, affecting flora and fauna, marine and terrestrial alike. By the time the dust began to settle, an estimated 75% of all species on Earth had vanished. Notably, this included all non-avian dinosaurs. The age of the dinosaur came to a sudden and dramatic end. But extinction was not the end of life itself. In the aftermath of the Chicxulub impact, new ecological niches opened up. Mammals, which had lived in the shadows of dinosaurs for millions of years, began to thrive. Their small sizes, burrowing habits, and diverse diets allowed them to survive where larger creatures could not. With the giants gone, they radiated into forms that would eventually give rise to primates, whales, and even humans. The Chicxulub impact is more than a story of death, it is a story of transformation. It reminds us that life on Earth is deeply interconnected and fragile, yet capable of immense resilience. The extinction of the marine reptiles, while tragic, also paved the way for the rise of modern marine fauna. Sharks, rays, and bony fish diversified and filled ecological roles once held by the great sea monsters of the Mesozoic. The fossil record preserves the stark contrast between the thriving ecosystems of the Cretaceous and the desolation that followed. Geological strata tell a clear story. Layers rich with dinosaur fossils are suddenly replaced with a thin band of clay, rich in iridium, rare metal more common in asteroids than in Earth's crust. This iridium layer can be found all around the world, offering irrefutable evidence of a global catastrophe. In some regions, impact spherulestini glassy beads formed from vaporized rock mark the immediate aftermath. These beads, along with shocked quartz and soot deposits, are forensic clues to the violence of that day. Fossil sites show mass die-offs of fish, abrupt changes in plant pollen, and entire ecosystems erased within what amounts to a geological heartbeat. And yet, amidst all this devastation, the seeds of new beginnings were sown. Crocodilians, turtles, and some bird lineages survived. They adapted and evolved. In the oceans, new groups began to rise. The early Cenozoic saw the emergence of the first true whales, the ancestors of modern cetaceans, who would one day echo the grace and dominance of marine reptiles in a new form. Today, the story of the Chicxulub impact serves not just as a scientific curiosity, but as a warning. It reminds us of the power of sudden global change. And in an era where human activity increasingly influences Earth's climate and biodiversity, the lessons of the past take on a newfound urgency. The marine reptiles, once rulers of the deep, are no more. But their legacy endures not just in fossils, but in the evolutionary blueprints passed down through time. Their tale is one of wonder, tragedy, and renewal. And it is one of the most powerful chapters in the story of life on Earth. As we unearth their bones and trace their ancient paths through now dry seabeds, we gain a clearer understanding of both what was lost and what emerged. In doing so, we connect our own story to a deeper history written not just in stone, but in the very fabric of life itself. The age of marine reptiles may have ended in fire and shadow, but their echoes still ripple through the oceans today.